Okay. The formula is integral. We introduce this new symbol. What means that? This is the line integral on the curve C, but this curve is closed. Okay, this is a new symbol. Okay, of the vector field dot product dr. Okay, so this is classical circulation line integral. Okay, you know, in 2 dimension, because Green theorem is in 2 dimension, guys. After we study another theorem in 3 dimension, but Green is 2 dimension. We can write like that, integral in the closed curve again, P dx plus Q dy. Remember, PQ are the component of the vector field. So this vector field, I suppose, que es P, Q. P represents the function, a scalar function, first component of this vector field, and Q represents the second. And the Green theorem say, wow, double integral in the region R. Okay, we want to explain who is the region R of the curve of this vector field dA. I put dA because I don't know si I want to integrate dx dy o en polar, ¿no? Ese double integral. So what is the interpretation of this? So we have the curve, closed curve, and Green suppose in your formula que always the orientation is counterclockwise. This is counterclockwise positive orientation. So in the formula, Green suppose que the orientation is counterclockwise, que is equal positive orientation. You say, bueno, profesor, si es clockwise, entonces what happens? Well, it's the same formula, but it's negative. It's negative. You introduce additional negative. This is a secret. And what about the region R? Easy. The region R is the area enclosed in this bone in the story. It's important to say something. To be valid, the Green theorem, it's obvious we need two conditions. No? The condition is a closed curve. That is the reason that in the formula you put this circle to indicate closed curve. And also PQ, que is a scalar function, are continuous. Que the majority of the example in physics, in engineer, the function are continuous and differential. So no problem with this. Okay? Entonces now today I bring a lot of examples of this. However, I have another version can the book never touch ROI. Okay, suppose that we have the same idea, but no. Let me right here down. No, I want here. Suppose now another possibility. Remember that we study the line integral over the vector field. Okay, we have two kinds. No? We have the circulation, and we have, for example, non-circulation flux integral. Flux integral is F vector field, but now not the R, is M ds. Remember, in the circulation, the R is a tangent vector ds. Another possibility is dx dy. In this case, in the flux integral, no participate tangent and participate normal, so no tangent, sino normal vector, because I want to find the flux, que es the amount of vector field que go out or in, depending the orientation that you want. Now I discover que M ds last class, ¿no? Es equal dy comma minus dx in the last class. Bueno, ese, according to the convention, this convention is in this orientation, so go out. Si es completely in opposite direction, well, you change the sign. Es minus dy comma dx. Okay, depende de idea. Pero bueno, suppose que es in the flux que leaving the curve. Entonces now, this is another thing I want to show you. It's a picture for me. So now, according to the, si you suppose again that this vector field is p comma q, and you suppose that this is this integral, and the curve is the notation we're using only in the line integral. You put c, indicate the curve. Is pdx, pdy, sorry, pdy per minus q dx. This formula you see before in the other class, no? We will practice a little bit example of this. Okay. So now, si I want to apply in this case the green theorem, so now I have double integral in the region R, get the region enclosed by the curve of the curve. But the problem is that the curve in 2 dimensions by definition is partial derivative q with respect to x minus partial derivative p with respect to y. But somehow in this integral is, the vector field actually is, you organize this integral like that. You put it in the same order of this. You put minus q dx plus p dy. You suppose that this line integral comes from, for the one vector field is minus q comma p. So you interchange intentionally like a vector field. So basically, the transformation behind it is that you want to compute the flux, you change a little bit the vector field in another orientation, and you see that the first component is minus q and the second component. So now, if you want to find the curve under this consideration of this idea, look at the formula, you differentiate q. Normally q is the second component of the vector field. So normally my vector field is p comma q. But in this case is the second component is p. Okay, so you differentiate p with respect to x, because the second component here is p. Minus in the formula for the curve, and you differentiate the second component is minus q with respect to y. Okay, let's do it. So now it's px double minus become positive qy. Wow, that means, suppose you remember this formula is divergence of the vector field f. Okay, so the version, the flux version for the green theorem, the books, I don't know why, never touch, is divergence here of the vector field, okay, of course, is a scalar function. This is also scalar, curve is a scalar in 2 dimensions, dA. Wow. And this is the green theorem applied in the flux integral. Okay, the beauty of the mathematics is that everything matching, everything is connecting, everything is logical. This is no logical. When you see your conclusion, you get the piece of paper, is no logical, it's because you are doing something wrong. So now, one interpretation is not the proof. Not the proof. It's not the proof. It's the interpretation. Geometric interpretation. I like so much. Because you are mathematician, but you are engineer, no? So for example, in this sketch, you can see the first version of the green theorem. In this case, the line integral is circulation. Entonces double integral of the one scalar function, que es the curve dA. Double integral. So now, to understand this, look, I make a zoom. Suppose que I chop the area in infinitesimal area. Of course, this is not infinitesimal, this is roughly sketch, but suppose que es infinity. Y en any, I put the point. And compute the curve in any point. And remember, the curve give me information about rotation of the vector field. Maybe actually in one vector field we have combination, no? We have the divergence, que es the flux que go out or in, depending if it's positive or negative. I don't care now divergence, I need rotation, a curve. Entonces you see that, for example, in this point we have a curve in this direction. And this point you have the curve in this direction. And you see how cancel out this. And cancel out in everything. Here, 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 and everything. And stay alive only the component of the curve on the curve. Physical interpretation. The other is cancel out. Now, if you addition every curve in the boundary of the area, que basically is the action of the double integral. Double integral is the sum, Riemann sum, of the curve of the vector field in the area. Entonces lógica. This is equivalent to compute the line integral circulation along the curve. Do you see or no? Tell me, guys, do you see or no? Beautiful. Likewise, likewise, something similar situation happened in the version of the flux. Okay, this is flux integral, I suppose. However, using green theorem is connecting with the divergence. And divergence, what is that? I don't remember very well. Divergence is, I make a zoom. Look, I make a zoom. We compute the divergence in any point. So you, one more time, we chop the area in one elementary infinitesimal. This is roughly a sketch. In the real life, this is infinitesimal. And the divergence is supposed to be positive, no? Is in this direction, in this direction, in this direction, in this direction. Entonces, you see how this component is canceled out. This component is canceled out. This component is canceled out. And stay alive only the version on the boundary. ¿Qué es this? Pero no circulation. Es flux. And likewise, green theorem summarize this like a double integral. So basically, divergence to stay alive, we condense it in this function, and you sum along the curve C using double integral. Wow, fantastic. Do you see the physical interpretation? Okay, cool. Now, Well, okay, I understand. But what is the importance? What is the application? Well, the application is the green theorem give me possibility to compute my problem in two possibilities. Or line integral or double integral. Suppose example like that. Suppose example like that. Suppose example like that. Suppose one example in which you have, this is two-dimensional, guys. Suppose one example in which we have a curve that is formed by different segments like that. Suppose this. C1, C2, C3, C4, and C5. So my curve C is the intersection C1 intersection C2 intersection C3 intersection C4 intersection C5. We have a pentagon, 1, 2, 3, 4, 5. So you compute this line integral. You need to break it down the problem in 5 problems. No? So basically, the line integral on the or along the curve C is integral C1 plus integral C2 plus integral C3 plus integral C4 plus integral C4. And look like long problem, no? Because actually we have 5 problems. However, si you apply the green theorem, you know that this is the double integral in the region R, and this is my region R. So you set up the double integral in the region R, y suppose que es easier, right? Y suppose que es easier. Entonces, always we convert line integral to double integral? No. Sometimes it's better doing backward. Suppose that you want to find the area of the one irregular lamp, like that, boom, 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 boom. Suppose that we have, I need to compute the area of this. Sometimes it's very, very complicated. Try to find the formulas or break it down in elementary pieces to compute the area. However, one fantastic way is long also, no? But it's another possibility. Compute the line integral. So basically, it's not exactly the perimeter. I want to explain it after. So you have, instead doing the double integral in the region R, dA, because I suppose the integral function is 1. No, you compute the line integral around the closed curve of the one special function that I want to explain in a few seconds. Okay, and you navigate not in the region R, sino around the curve C. Entonces now I know que es no short problem, it's complicated problem, pero es relatively easy. So you don't care the part inside, sino the part outside. There are connections in between line integral and double integral. Okay, entonces now let's see example to the application green theorem. I suppose que not too much, because today I want to start another topic. Pero enough. Remember in the review package, que I suppose que es next week, we'll go over again to everything. Okay. Any question, guys? Do you follow me? You get the basic idea. No in detail, no deep, but in the basic idea. Okay, let's move on to the example. No, the example is super good because it illustrates the application. Suppose I need to compute in example 1. I need to compute this line integral. Remember that symbol indicate closed curve of the x to the 4 power dx plus xy dy. And who is C? Well, C is curve formed by segment like that and like that, form a triangle. Form a triangle. So we have one first segment I want to call, and the orientation is C1. This is 0, 0,0, and this is 1,0. And this point is 0,1. Okay, and the orientation continue here, C2 and C3. Okay. Entonces we can compute this, separate this curve in three curves. I compute the line integral from 0 to 1, to 1 to 1, diagonal here. But no. Let's do it using Green Theorem, and we take advantage the region R. Is this. Okay? Okay, first of all, I need to understand where's my vector field. Okay, generate this line integral circulation, I suppose, que circulation, because of plus. I don't know. So now the vector field is so because this guy P and this guy Q. The vector field is x to the 4th power, comma, xy. This is the vector field. Okay, now immediately I make a decision to apply Green Theorem. And Green Theorem somehow involves the curve. Guy, to be familiar, remember curve is in the nabla notation, nabla cross product F. Little by little. And 2 dimensions is not extremely important in this notation, but it's okay. And the formula is qx minus py. Okay, this is p, and this is q. Partial derivative q with respect to x is y. Minus partial derivative p, que es x to the 4th power, with respect to y, es 0. Oh, es y. And the curve is y. Okay, entonces according to the Green Theorem, you set out double integral in the region R of the curve of the vector field dA. In our specific problem, it's double integral of the y dA in the region R. Cool? Now, you are strong doing double integral, no? Because you passed the chapter 3. Let me try. It's obvious que we are using Cartesian, no necessarily polar. Polar is when the region is circular, something like that. Entonces now you say, bueno, professor, what direction you will prefer? I prefer always this direction of the integration. So my double integral is y dy dx in this order. Now this go from 0, que es this, to this, que this is the equation for the line. Okay, by the way, this line is x plus y equal 1. Therefore, you isolate the y, is 1 minus x. And when you open the window in that direction, I go x to from 0 to 1. And you solve in this double integral, and the answer is 1/6. Boom. I compute this line integral with the transformation double integral. And this is possible because it's a closed curve, and see it's open now. See it's open, you need to do step by step. Okay? Okay. Any question? Do you follow me? Do you follow me? Okay. No problem. Let's move on to example 2. In example 2, I bring a new situation. In example 2, I want to explain something. Well, before the example 2, I want to explain something. I want to explain. You have this formula que representa the green theorem. I want to copy again. Double integral in the region R, a curve, the curve is qx minus py dA. This is the curve of the hypothetical vector field. Entonces I want to use the green theorem, but in another direction, in another goal, another point of view, is compute the area. Compute the area. So I want to compute the area. One of the logical ideas to compute the area is double integral. But you know very well the meaning of the double integral is a volume. However, si the integrand function es 1, o sea, si yo artificially I guarantee que this is equal 1, it's obvious that this is the area. Si es 1, there are many combinations, no unique combination, but one fantastic combination, the frequently, the often combination que es using is suppose que qx is 1/2. There are some another combination, but that's the most popular. And px, py, sorry, and the curve is negative 1/2. It's obvious that 1/2 minus negative 1/2 is equal. This is one possibility, not the only. You suppose that this is 1, this is 0, or another possibility. Okay, but this is the most popular. Therefore, si you apply antiderivative of this, in order to find the q, so you integrate with respect to x is 1/2 x. And you apply antiderivative with respect to y, p is equal negative 1/2 y. Okay, cool. Entonces now substitution. Substitution where? Substitution here. O sea, the line integral es p, pero p es negative 1/2 y dx. And q is positive half x dy. Let me try to manipulate to put more elegant this equation. Now this equation I factor out 1/2 outside. Line integral in the curve C, this is 2. And you copy x dy, que es that part, que es the positive part first, minus y dx, que is the negative part, secondly, and this is area. Wow, look at that formula. That formula, instead doing the double integral, no, we are doing the line integral along the curve, and we compute the area enclosed this. It's another possibility. So we have flexibility. We can compute the area, no try to find the formulas. Or you fighting inside the, no. You're moving along the curve like a perimeter, and using that formula, boom, you get compute the area enclosed and the closed curve, of course. I bring one example, super easy, but you can apply a more complicated example using that formula. Suppose I need to find, look, a curiosity, example 2. You need to find the area. Find the area of ellipse. Because I don't know the formula for the area for the ellipse. So basically, we have ellipse. Here I need to find the area of the ellipse. Okay, so I know very well, very well, the area for the circle. Area of the circle are familiar with the formula, geometry. And the circle is easy because we have radio that is always constant in any direction, and the area is pi, radius square. I am familiar with this, but I don't know what is the formula of this. Suppose the ellipse que es horizontal. x squared over a squared plus y squared over b squared equal. You know very well in pre-calculus, this segment is a semi-major axis A, this axis B. And this, I suppose it's different, no? Because it's elixir, no? It's a reason que es elixir. Okay, no problem, I understand. So now I use my famous formula, that formula. I try. But remember, to compute any line integral, you need the parametrization, the curve. But parametrization is super easy because you call, for example, x is equal a cosine t, and y is b sine t. And you know that this parametrization matching perfectly because you divide by a and divide by b and square both sides, you have cosine squared plus sine squared is 1, and this is described perfectly the elixir. Okay? And t vary from 0 to pi because I want the full elixir, no one portion, no one R length. Okay, but my formula involves not only x and y, involve the x and dy. So you differentiate derivative. Well, actually it's differentiation, no? Es derivative, pero expressing like a differential. Entonces dx es igual, derivative cosine es minus sine. Entonces minus a sine t dt. If you, for example, guys, you put d differential, you put d, you ending in d also, no? You know that, calculate. And likewise, dy es the derivative de second, que es derivative sine cosine. Entonces b cosine. Cosine t dt. Okay, entonces plugging in. Where? In the formula. The hypothetic area I try to find is, look, the hypothetic area I try to find is area 1/2 integral. Well, remember, you convert this line integral in one ordinary integral like a calculus when you are doing the parametrization. This is the magic of the parametrization. When you are doing the parametrization, our line integral magically is converted in the ordinary integral, que in this case the parameter is t, and t go from 0 to pi. And you copy step by step. Who is x? Is a cosine t, a cosine t. I copy this part. dy. Who is dy? Oh, dy is b cosine t dt minus y. Who is y? Y is b sine t. And who is dx? Dx is minus a sine t dt. Wow, the rest is easy. Multiplication. Es obvio que you see que es area is equal 1/2. And you see AB together, right? AB cosine square, AB cosine square, T. And it's a plus because negative and negative, double negative, AB again sine T, square T, dt. Don't forget dt, it's common here and here. I put outside like a common factor. Entonces I factor out AB because it's a constant, ¿no? Entonces AB divided by 2, integral, I forgot the limit, 0 to pi. I inside stay alive, cosine square plus sine square, I get 1. Actually is integral from 0 to pi of dt. Integral dt is t, evaluate in between 0 to pi is 2 pi. So the answer is AB over 2 times 2 pi. And 2 is cancelled out, and the final answer is pi a and b. This is an example, trivial example, to illustrate the power of the line integral to compute the area inside this. So instead of moving inside the figure, you move around the perimeter. and you compute the area. Cool? Cool? Any question? Any question? Any question? I do it too fast. I do well. Eh? What's going on? Okay. Guy, help me. Say something. Good, no? Let me see where my laptop. This Max is clear. Okay, okay, okay. Erase everything. Inside the green theorem, I want to explain another idea. So basically, the curve we are using in this problem is simply connecting. Okay, let me change a little bit to 3, much better. Yeah, simply connected curve. Okay, simply connected curve is just one simple connected. So no, there are no only one curve. See. However, we have no simple connecting curve. For example, this. You have a curve and you have another curve inside. You have C1, C2, C3, C4. And we can apply green theorem? Yes, you can apply. I want to prove now. To prove this, I suppose, not too complicated, I suppose a little bit more easy. Suppose we have one curve. Okay, I want to call C1. You have another curve inside. Okay, I want to call C2. Important. The curve outside is counterclockwise, and the other is clockwise. This is the idea, to get the result perfectly using green theorem. And of course, the area, the region that we are talking about is, of course, this region. So not totally crazy, not totally arbitrary. So to apply the green theorem, well, the consideration is, yeah, you can. Of course, I want to show you one example. But the curve outside is counterclockwise, and the curve inside is clockwise. See, both are clockwise or counterclockwise, those are different signs, and you cannot apply the green theorem directly. Okay? Entonces now, okay, well, let me try to understand this because it's confusing. To understand this, I propose you to separate artificially this and two curves. The first curve is this. Look. And the second is this. Okay. And we travel, for example, here. This is C1. And I suppose que C2 is in this direction. No? And this I cross this and separate. Right. So you compute, for example, the line integral and the new curve, que is this curve. I'm using blue curve C1. We go here, we go here, we go here. Perfect. And we compute the another in this direction. Let me see this direction, this direction. and this direction. Es obvio que this is equal and opposite sign and cancel out. The thing I try to prove is que the blue and the green together is equal to this. Okay? Under the consideration que the outermost is counterclockwise and the innermost is clockwise. And si es opposite sign, si es opposite direction, maybe green theorem or no apply or apply with the opposite sign. Depende, no? So, I don't suppose que C1 is clockwise and C2 is counterclockwise. You can, but you change the sign of the green theorem. However, see, both are in the same direction, no. Okay? Ese example, easy example. Suppose que I need to compute this example 3, no? Example 3 computes this C integral, compute C of the 3x minus 2y dx plus x minus 4y dy. And who is C? Bueno, C is the ring. C is the ring. It's the ring like that. Look. It's the ring formed by one circle here of the radius 1 and another circle here of the radius 4. Y our famous region is this. Of course, the direction of this non-simple curve is, this is C1 que es counterclockwise and this is C2 que es clockwise. And this is my famous region R. Entonces, we can, so C, we see, C is C1 union C2. Okay, we magically, for example, at one point you deviate the attention, go here, continue around here and return. You have that direction, and cancel out. And you not necessarily 1 point, 2 point maybe, no? So you travel this direction, and you return to this direction and continue here. Okay, so I don't care this part because parts cancel out. I focus in the non-simple connecting curve. So it's two curves separately, but artificially, mentally, in my mind, I can connect it using the segment. But I know in this segment, the line integral is the same value and opposite sign. So don't affect my answer. Okay, so first of all, I need to identification my vector field. My vector field es obvio que dice P, es obvio que dice Q. And my vector field is 3x minus 2y, comma, x minus 4y. And immediately I compute the curve of this vector field, que the formula in two dimensions is easy, as partial derivative q with respect to x minus partial derivative p with respect to y. Sorry. And partial derivative q, this is p, and this is q. Partial derivative q with respect to x is 1, because we have only one x here. And partial derivative p with respect to y is minus 2. So be careful with the sign. We have a minus here, and the partial derivative p is minus 2. Minus 2. Entonces, the minus, double minus positive is 3. The curve is 3, it's equal 3. Okay? According to the green, we can transform it, this line integral, and another double integral in the region R. Mathematically, it's equivalent. Therefore, see, I complicate, I see it's too complicated my work doing line integral, and it's relatively easy to compute this like a double integral. So I decide switching my problem to the double integral. And the core is easy, is 3. And this is the A, no? Okay, look like fantastic. Now, I try. Okay, this is you can using geometry to compute the area because it's the big circle minus the small circle. But okay, suppose I don't see very well this, no problem. You are doing by the traditional way, case you convert my problem in polar, no? Because it's a circle, no Cartesian. No integration in this direction. No. It's stupid. Integration in polar, okay, you know, in polar is in this direction, no? Entonces now my double integral is 3. It's the integrand function, constant. You put outside if you want. I make a decision to polar. Jacobian, RDR, detail. And R go from 1 to 4. Look, 1 to 4 is a ring. And theta go from 0 to 1 because it's a full circle or full ring. And now you can separate because remember the limit constant. We can separate separable variable. No, 0. No. This is 1. 1 to 4. Now this is 2 pi. This is 3. This is 2 pi, obviously, no? And this no. This is r squared divided by 2, evaluating between 1 and 4. So this is 16. So 4 squared, 16 divided by 2, 8. Minus 1 is 1/2. 15 over 2. No, because this is 16 over 2. Minus 1, 15 over 2. So 15 over 2. The 2 is cancelled. And 15 times 3 is 45. 45 pi. Is the answer for the double integral is equivalent, is the same numerical value of the weird, complicated line integral. At the beginning, I don't know how you are doing. Okay, one more example. I'm from again in the review package. We go over again to the green theorem. One more, example 4, and that's it. Any questions so far? Everyone follow me? Okay, good. Let me try to summarize the idea. This is science fiction. This is magic. Green theorem give me a connection between line integral and double integral. If you are strong doing double integral, don't hesitate to switch into double integral to compute that. What is the only restriction? It's a closed curve. See, the curve is not closed, it's open. You cannot region, it's obvious. Therefore, we cannot apply green theorem. Okay? Let's move on to the last example. Example 4. Compute this y squared dx plus x squared dy. And who is C? C is the region. Normally, the region is, or the curve is represent graphically or no, mathematically is look, let me show you. Is this segment C1, this segment C2, this segment C3, and this segment C4. In this direction, counterclockwise. And the dimension for this square, because actually this is a square, is 0,0, this is 1,0, this is 1,1, and this is 0,1. Okay, it's a square. Yeah, our famous region is this, it's a square. And by the way, the area of this square is 1. But remember, you convert the line integral and double integral, but you have inside the double integral no one like an integrand function. So you have the curve of this vector field, the hypothetical vector field. Okay, entonces now let's do it. The idea is, you are doing using the idea for the line integral, we need to split this line integral and 4 line integrals, C1, C2, C3, C4. This is disadvantage, and this is the idea for the green. Green is good and close, and when you have different pieces, you say you need to separate your problem in the one problem in 4 problems. However, I condense it in double integral and the region. Okay, first of all, vector field. Vector field is, this is P and this is Q, I suppose. How you identify it? Because the guy gets in the same formula for the dx is P, entonces P is y squared, comma, and Q is x squared. Cool. This is my vector field. To find the curve in 2 dimensions is super easy. The formula is qx minus py. You differentiate. This is P and this is Q. You differentiate Q, que es x squared with respect to x to x. Minus, you differentiate P with respect to what? X to y. This is my curve. Okay, no 1. Si es 1, entonces es the area. But in this case, no, it's not 1. Entonces you convert my problem automatically in using green theorem and double integral in the region R. The integrand function is 2x minus 2y dx. Okay, it's easy. If you want, you factor out 2 outside. Oh, no, the algebra is not important. The important is set out the limit, you know? Okay, so this double integral is x minus y. Yeah, I suppose, as always, when there are no restrictions, I suppose the orientation of the integration, I like so much this, like that. And to do integration for respect to dy first, and dy go from 0 to 1. And finally, when you open the window in that direction, I go x from 0 to 1. This is super easy to compute that. I will not skip this, but you know that. The answer is unbelievable. The answer is 0. Wow. So I bring this example to illustrate one idea que es confusing, very confusing. The idea is, let me explain. When you have conservative vector field, a curve is 0. Entonces es obvio que si yo apply Green theorem, the integrand function is 0. And the integral double integral 0 is 0. There is no contradiction. This is a confirmation that the line integral and the closed curve in the one conservative vector field is 0. Remember, so now the reason is because this vector field confronts with the gradient of the one hypothetical potential function. I want to find the potential function, y I evaluate the potential function, no? But in this case, no necessarily evaluate because in the closed curve is 0. Es obvio que the potential function in the point and itself is la difference is 0. However, in this problem, this vector field is not conservative because the curve is not 0. However, the integral is 0. This is coincidence. No, it's not a fact. It's a coincidence. So, si es conservative, the super fantastic conclusion I want to discuss now, si es conservative, imply that the line integral in the closed curve is always 0. However, the converse statement is not true. Sometimes happen que es 0, however, the vector field is not conservative. Cool? Any question? Please.
So this vector field was not conservative?
Absolutely. How do you know que no? Because the curve, to be conservative, mister, the curve should be 0. Should be no, must be.
But in this case, x or 2x minus 2y.
Maybe in one point is 0. Maybe in one point is 0,0. But in other point, no?
Yeah.
The thing I want to discuss is que si the line integral de closed curve es 0, no necesariamente happen que the vector field is conservative. Lo que sí es necesario que happen is in the opposite direction. Si you discover in the middle of the story que the vector field is conservative because the curve is 0, automatically the line integral is 0. Okay? Are you agree? You understand very well the idea, mister?
Yes.
Excellent. Beautiful. That's the thing I try. Cool. Okay, now we spend the time in the super important, interesting part now. I switch and forget about, for a moment, line integral. For a moment, forgot about line integral. Let's discuss it in detail now. Parametric surface. Wow, what the hell? Parametric surface. Let me recall something you know very well. You know very well how we can parametrization a curve. Suppose 3-dimension environment, 3-dimension context, 3D. However, we have in 3D one dimension object que is a curve. The dimension for this object is 1D because it's a curve. But the curve only have our length. We have no width, we have no height, only one dimension. However, this living in the 3-dimension context, no problem. Everyone understand this? Do you understand very well the difference between dimension of the object and dimension and what you consider it is to be it? Okay, now are you super familiar que to apply the vector cálculo and you apply line integral, you parametrization the curve? How? Well, okay, you create the parametrization. You create, for example, a vector value function que contain only one parameter, que es t. And this vector value function have 3 components: xt, yt, and ct. And t vary, for example, to a to b in general. Entonces, in this point, I have, for example, the point P1, suppose que es the point x en A, coma, y en A, coma, c en A. Ese point o vector. Either way, si you consider like a vector, entonces actually it's the vector position, que es this. Likewise, this is happening in B. So this is at t equal A, evaluate here, A, and t equal B, evaluate here. And this is described perfectly. This mathematical idea describes perfectly our portion of the curve, even the orientation. Because I suppose that A is the start point and B is the end point. Cool? Do you remember what this is, right? Yes or no? We're working a lot, not too much, but we're working in the chapter 2 and we continue in the chapter 4 with this idea. Now I want parametrization, no curve anymore. No curve anymore. No curve anymore. We parametrization surface now. It's the same idea. is a vector value function, but in this case, the vector value function contains two parameters. Not t. T is a one dimension. It's two dimension. I want to call generically u comma b. After I promise I change the letter to the specific thing is more understandable in a specific example, no? But in general, it's two parameters, u and b. And you have the vector value function to represent the first function I want to call x. Exactly the same I call x here, I call x here. Que es a function u and b. Y u and b. C u and b. And that's it. No. Like y here, you represent domain of t. Okay, by the way, this domain is one dimension. So you want to graphic, to understand graphically, this domain is one line, one dimension. This is a line that represents t, and this varies from A to B. So this domain generate this line. In this case, no, because we have two variables, u and b. So my domain is more complicated. Domain is, for example, u vary from A to B, and b vary maybe from C to D. And the representation is domain is in the new plane UB. Remember, this is the line T, this is the plane UB. You have a square or rectangular, maybe, no? This is AB and this is CD. Okay. And any point inside this rectangle, when you plug it in the vector value function in two dimensions, generate in the three dimension context. A surface. A surface. Okay? For example, that point is this point. For example, that point is this point. I don't know. Exactly. Let's see in the elementary example. But the most important is que in this case, you convert this problem que es three-dimension, pero two-dimension object, because surface is two-dimension object. So I suppose que the thickness of the surface is negligible, no? So surface have maybe length and width, but not height. The thickness is zero or negligible, zero. And you convert this surface que es curvy and one que is completely flat, okay, in another domain, UB. This is very, very similar, little bit. I want to dedicate one lecture after, when you finish everything, even the review, to understand much better this idea, when the substitution, when the parametrization. Okay. So now, this is theoretical part. Okay, this is 2D domain, but now it's flat. Okay, let me see example, and also I try to find, I create a script in Geogebra to understand much better this. And I promise I emphasize too much in that part because this part is super, super important. Look. Suppose example 1. Example 1. Suppose case given this vector value function in two dimensions. It's a b cosine u, comma, b sine u, comma, b. And the domain of this is, for example, b vary from -5 to +5, and u vary from 0 to pi. Es lógica que u, ese parámetro que es angle, because it's inside the argument of the trigonometric function, no? And b no, b es supposed que es distant, no radian, es centimeter, inch, whatever. Okay. Entonces now, si yo describe, or you try to understand this idea of the domain of the parameter graphically, I like so much graphically, you see that we have a rectangle. And the dimension for this rectangle is 0 and 2 pi. And the dimension is +5, -5. And this is my region. And this is my region, my domain of this vector value function. Just now, the thing is, how you see that? How you see that in the three dimension, no? This is the challenge, you know. How do you see that surface in 3D? Chan, chan, chan. Okay. I don't want to waste the time to explain because it's a little bit complicated. However, I suppose you remember very well when you study the parametrization for a curve in 3 dimensions in Geogebra. You have the function curve, and the syntax of the function curve is in 3 dimensions. You have function x, you have the function y, you have the function c, you have the parameter t, you declare the name of the parameter, and you declare the domain, you know, from A to B. Okay. Now in Geogebra we have another function que es surface. Wow, fantastic. In parametrization. And you declare exactly the same. You declare x, you declare y. Of course, this x is like a function ub, no? This is a function of t, this is a function of t, this is a function of t, no? Entonces, this is y like a function ub, no? C like a function ub. You declare the first parameter u, que in this case is this guy, and the range f0 to pi, comma, and the second parameter que es b, you declare the name inside the equation, comma, -5 to +5. Bam! And when you press enter, you see a cone, double cone. Double cone, que this double cone is completely circular, no? So, because it's from 0 to pi, and this high is phi, and this high is -5. I want to show you. No more blah 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 blah. But this is super important. Let me try to open Geogebra, and I try to find the script to describe this. Okay, I create for you. When the class is over, I send. Okay, open. Okay. Area, line, parametric surface. Okay, there you go. And this? Yeah. Okay. Let me share the screen. There you go. Do you see Geogebra? Window? Do you see? Excellent. Look there. Focus it in this. I put any arbitrary A, B, C, D, and you put the command surface, and the command surface contains 3 functions. The first function is b cosine u. comma, B sine U, comma, B, just P, comma U from 0 to pi, and B from -5 to 5. And you see that? Boom, look at that. A second. Okay, you have the habit to identify a cone or a sphere or something in the classical graph XY. But I discovered a new way to visualize the graphic. Okay, at the beginning it looked like more complicated, but it's super useful for the thing we are computing after that. Okay, do you see that or no? Do you understand the idea for the function surface and Geogebra? Yes or no? Come on. I need to comment. Any questions? Do you see or no?
Yeah, we see.
Ajá. Okay. Entonces now, I don't like too much. I don't like too much the letter UB, because UB is nothing. UB is, I don't know. It's generical, no? However, in my opinion, in the problem of the example one, I prefer, let me erase that part. I prefer call different. I prefer to call R and theta. Because actually, oh, yeah, R and theta. No UB, R and theta. Because I know that U is angle. And notice radio is maybe the high, but it's okay. I call in the paper. The name is not important. To see more physical idea or more logical idea. This is R cosine theta. This is R sine theta. You know the name, and this is R. The name of the verb is not important. You put Maria, Jose. This is equivalent. This is the same. So you declare, of course, the theta vary from 0 to pi, and R vary from -5 to +5. What's happening in the Geogebra? We have, but it's weird, the Greek letter, theta, something. So I prefer U and B. Okay? And when you go to Geogebra, this is my way. No, I respect, maybe you discover another way. You discover in Greek letter, it's okay. So the name is not important. But when I'm working in the piece of paper, I prefer call R, theta, phi, the usually name of the variable that we work on cylindrical coordinate or in spherical coordinate or in Cartesian coordinate. Okay, XY is possible also. Okay. Let's move on to example 2. Wow, time flies. Example 2 is very, very interesting because you have this surface, x squared plus y squared plus z squared equal 4. Who will be able to identify this surface? What kind of surface? Help me. Hey, are you there? Or you are sleeping?
The surface on the screen?
What's that?
Are you asking about the surface on the screen?
Okay, you see whiteboard or no? Sorry.
No.
Hello. Sorry, I'm crazy. My big problem is I focus on the mathematical part. I forgot. Wait a second. Cancel here. Okay. Share. Come on. There you go. Do you see whiteboard now?
Yes, we see it now.
Super. My question was, I copy in the example to x squared plus y squared plus c squared equal 4. So my question was, what kind of surface it is? Can you very well know?
It's a sphere.
It's a sphere. Super cool. It's a sphere. It's a sphere. However, I want to discuss it the best way to do the parametrization of this surface. Because remember, what is the idea? In the future, we are working with the new thing that we need parametrization. Okay? We need parametrization. So now, well, one fantastic way is using a spherical coordinate. A spherical coordinate. Because it's a sphere, ¿no? Makes sense. Entonces X, I copy the equation, I copy the formulas for the sphere, the spherical coordinate, sorry. Remember que es rho, sine phi, cosine theta, something, ¿no? Pero rho, in this case, by the way, the radius of this sphere is 2, ¿no? Entonces you transform a little bit. Entonces es the radius 2 sine phi cosine theta. And y is 2 sine phi. So we are doing nothing new. It's the same formulas of the spherical. The only thing the idea was declare que rho is 2, ¿no? Because the radius is 2. I put 2 here, no rho, sino 2. When you put rho, it's because rho is a variable. And generate another. And this is cosine. Wow. Entonces now I create the vector value function que dependen de tu parámetro, que es phi and theta. In this case, is no UV, is phi and theta, que es the parámetro que we see in the equation, phi and theta. And the vector value function is, in the first component is 2 sine phi cosine theta, comma 2 sine phi sine theta, comma 2 cosine phi, and that's it. So you copy here the expression for the x, you copy here the expression for the y, and you copy here the expression for the c. That's a function of the two parameters que phi and theta. So what about phi and theta? Suppose I want the full sphere. Okay, you see a full sphere, phi vary from 0 to pi. Pi, not 2 pi, pi. And theta vary from 0 to pi. And this generate full sphere. And the domain, if you want to see graphic, I like so much doing this sketch. Why? Because in the future, we're using this sketch. I promise. And the domain is 0 to pi, 0 pi. And this is my region. Okay, I suppose que we use it in the future. Okay. And it's fantastic. Wait. Entonces now, wait. Bueno, let me show you curiosity. Let me show you Geogebra. Share screen to Geogebra. Do you see Geogebra? Oh no. Do you see it? Excellent. Entonces no con anymore. Nice sphere. Bam! Look at that. I copy the weird equation. Of course, I use no Greek letter, phi and theta. I use U and B. Doesn't matter. The name of the variable is not important. And you declare, for example, The beauty of that part is that we have more degree of freedom. Suppose I want to change no from 0 to pi. Look at that. Let me make it 0 to pi. I change from 0 to only 1 pi. I delete this pi. All right, let me see. No, coño. Ah, bueno, pi is pi. Pi in Geogebra you put capital P and I. It's a pi. Okay, suppose my intention was in the keyboard I make a mistake. No? I delete no pi's, you know, I delete 2. I press back. I press enter. Bang! And you see a half of the sphere because I vary b, que b I suppose que phi from 0 to pi. A ver, let me see. Restore again pi here, 2 pi. Over here. Okay, moving. I put 2. Press enter. Again, full sphere. Suppose I change u, no in pi, you know, in pi over 2 divided by 2. Press enter. You see, wow, what the hell is that? Okay, you can do a portion of the sphere. Okay, in the traditional way, without parametrization, we cannot do that. Okay, you put the x squared plus y squared, like that, look. No, I have no here. But you have the sphere, no? X squared plus y squared plus c squared equal 4. And you see the full sphere, not one portion of the sphere. So you can manipulate more you know, details. I need the hemisphere or quarter of the sphere or whatever you want. And you have more accuracy about the surface parametrization. Okay, again, restore the full sphere. Okay, do you understand this or no? Okay, let me try one more example, and that's it. We continue Friday with the parametrization and the application of this. Okay, and the application. Example, okay, I go to whiteboard. Do you see the whiteboard now? Example 3. Example 3. Do you see whiteboard? Yes or no? Let me know.
Yes.
Okay. So now we have C is equal 4 minus x squared minus y squared. Semicolon, C is positive. Or 0. What kind of surface it is? Help me. What kind of surface it is? No parametrization. Using your knowledge in the chapter 1.
It's a cone.
No.
Or cylinder.
No.
2 sheet.
No. Okay. When you see a C, it's okay. Con
the paraboloid.
Absolutely, no. Si no es Juana, es her sister. Okay. Es paraboloid. Okay, paraboloid. Along, what axis? Along.
Z.
Exactly. You open up or open down?
Down.
Down because negative. Good. And the what is, by the way, the Z intercept? So what is the value of the paraboloid open down? It's the 4. Z in F4. Super cool. This is my roughly sketch about paraboloid. Of course, it's around, so it's completely around because there are no limitations for the X and Y. Limitation only the C is stop here and still. Okay, cool. Now, what is the parametrization is? The parametrization is r theta, or ub, either way. And this is r cosine theta, comma, r sine theta. And this is logical, right? This is the expression for the x. This is the expression for the y. And the expression for the c is exactly this expression, pero using the parámetro, ¿no? Que es r and theta, que es 4 minus r squared. Make sense? Because x squared minus y squared is r squared, no? So you factor out negative here. Make sense, guys? This is c. Of course, this is 4. Make sense, right? Yes. Daniel said yes. Now. What about the domain of this parametrization? This is super important. The domain is, this is theta, suppose. In a way, you copy one axis theta, one parameter, another parameter is r, no? Okay. Entonces now, this very from 0 to pi, because it's completely circular paraboloid, no? And r very from 0 to 2. 0 to 2, 0 to 2, to 2, here. And this is my domain. Okay, yeah. Because 2 squared 4, no? Okay. So this is my, you can represent like that graphically, or you can represent like that, no? Theta very from 0 to pi. And r very from 0 to 2. This is equivalent to C graphically, no? And this is my region R. Okay, I promise que we ending in double integral, because we are studying next time surface integral, que es the last integral que we study, no more integral. It's another version of the integral. But we studied so far double integral, nice. Triple integral, nice. We studied line integral, nice. But we study now surface integral. And this surface integral, to solve it, to compute, to understand the meaning of that, we need the parametrization of the surface. And we ending the surface integral and the conversion to the double integral and the region R. And this region R is this region R. Okay, I want to finish today. We continue next time with the parametrization of the core and the application to see the paraboloid in the Geogebra. To see the paraboloid in Geogebra. Paraboloid. Okay, paraboloid in Geogebra. Paraboloid in Geogebra. That was the sphere, right? The third example is the paraboloid that I copy B, no R. R cosine theta is B cosine U, comma, B sine U, comma, 4 minus B squared, gets 4 minus R squared. Look at that. One, paraboloid. Paraboloid along the z-axis, up and down, intersecting 4. It's another way to visualize this. Super useful, super powerful. Okay? And my plan is, I don't know. Say I finish. So we have, okay, this is 13. We have 2 weeks. So I try to do my best Friday and Monday to finish everything. And we spend the rest of the time, I don't know if it's possible, doing the review. At least 2 lectures or 3 lectures for the review, to discuss everything in detail. Okay? And send to you soon the test number 4. Reading test number 4. Okay, guys? Cool? Cool?
Mm-hmm.
Do you understand the new idea for the parametrization surface?
Yes.
It's logical? Yes. Makes sense?
Mm-hmm.
Entonces I want to send the video, but I want to send also the link connected with the script of the Geogebra. You open a home and you try to manipulate, edit, don't hesitate. Remember, you receive a copy. It's not mine. So you can. It's important that you understand. And in the review, in the another example, I emphasize the surface command in Geogebra. Surface. Do you see this command that we use in double integral and triple integral? Do you remember? But I never explained because we are not ready to understand this. Now this is a moment to be ready. Okay? Cool? Okay, bye. Entonces now, bye. Thank you so much.
Professor, before we go, I have a question about the last exam.
What marks exam? We have one officially, test number 4, and that's it.
For
Test number.
I received a 0.
Say again.
For the last exam, I got a 0 for my grade.
Well, okay. Particular situation. Well, who are you, Mister?
Oh, Daniel.
Daniel. Email me, Daniel. This is not the place.
I send you an email, Professor.
Ah, really? Well, send me email again right now.
Okay.
Okay?
Perfect.
Bye.
Sounds good. Thank you.